if you're going to build a building out of timber, you need some design values to use in your calculation to ensure that the building is safe. You need values for strength, you need values for stiffness. The process by which you guarantee that the timber that you use has those design values is called strength grading. Sometimes it's referred to by its old name of stress grading, but the modern term in Europe is strength grading. And strength grading is guaranteeing three main grade determining properties, which are strength, which is usually either from bending testing or tension testing. For normal construction timber, it's based on bending testing. For glulam, often it's based on tension testing. So one measurement of strength which we can establish from testing. And stiffness, that's the second grade determining property, obtained from the same kind of test. And the third grade determining property is density. There are many other design values that you need to do a full structural design, but those are calculated. They're called secondary properties, and they're calculated from these three primary properties by conservative equations. So things like compressive strength perpendicular to grain are estimated from density. So how do we do this? How do we guarantee that the timber has the properties that we expect it to have, these three grade determining properties, and how do we describe those on the market? Well, we describe those combination of those three grade determining properties by means of a strength class, most commonly. And a strength class is just a shorthand way of describing that combination of properties, a certain expected strength, a certain expected stiffness, and a certain expected density. And most commonly we're referring to EN338 strength classes. That's the standard that contains things like C16, C24, D30. Strength classes for softwoods and hardwoods, although these days you can put hardwoods in the softwood classes. Anyway, these are just shorthand ways of describing this combination of strength, stiffness, and density. And in fact, your strength class doesn't need to be one of the ones listed in this standard. You can use another strength class as long as the market understands it. You can make up your own, or you can use an already existing one that the market knows. TR26 is an example of a commonly used strength class that doesn't appear in EN338. It's a strength class for truss rafters used in the UK, and many countries in Europe produce timber of this strength class. So actually, how do you do it? How do you go from some timber to having a set of timber with a certain strength class and guaranteeing that those design values so that buildings can be safe? Well, there are two main ways of doing it. The old one is visual strength grading, and that's based on things that you can see about the timber, and you're quite limited in the things that you can see. They are things like the size and shape of the knots, the ring width, the slope of grain, that sort of thing. So things that are measured by a trained human being. So that's visual strength grading. There is another system which is called machine strength grading. And machines potentially can measure many more things than a human being can. A machine might, for example, measure the density with an X-ray. So machine strength grading and visual strength grading. Visual strength grading is separate from appearance grading. So appearance grading is when you're looking at a piece of timber and you're accepting or rejecting it according to certain things that you don't want. Perhaps you're making furniture and you don't want knots, so you might appearance grade it for knots on one of the surfaces so that you can have a nice good finish on your furniture. But visual strength grading is separate, although there are a few special cases where an appearance grade will go and work the same as a visual strength grade. French oak is one example of that. The reason why appearance grading doesn't work as visual strength grading does is because both of these systems need to have been based on mechanical testing. We need actually hard evidence of these values: strength, stiffness, and density. We need to have done some tests in order to be able to assign strength class via grading. Now, both of these systems are based on the same underlying principle, which is controlled by the harmonized standard EN 14081. So that applies rules for both visual strength grading and machine strength grading. So visual strength grading is often done to national standards. So they are like French standards, German standards, rather than European standards. But those national standards need to follow the rules of the European standard. The reason that we still have national standards for this kind of thing is that growth conditions affect the visual grading in such a way that we can't make a good, useful visual grading standard that works for all of the timber in Europe. There are differences by country because of the way that growth conditions affect the correlation between visual criteria and strength class. So yeah, that's visual strength grading and machine strength grading, and they're really both working on the same principle underneath, and that is that we have some relationship between the grade determining property that we care about, so that would be something like strength, stiffness, density, and the thing that we can measure in the grading, which might be size of the knot in the case of the visual strength grading, or it might be stiffness of the timber in the case of machine strength grading. So we have something of a relationship between the two, so we can draw a relationship, but it's not perfect, so there is a cloud of points. We would like to be able to sort the timber according to the thing that we care about, the grade determining property, but we can't do that. We can only make decisions based on our indicating parameter, knot size or measured stiffness value. So we can only make decisions based on this axis. And the whole idea of grading is that we find a threshold that divides the population up in such a way that we separate out the poor timber from the good timber. And for strength, it's the low values that we care about. So it's the lower fifth percentile. So on this side of the grading threshold, the lower fifth percentile is around about here. And on this side, it's around about here. So even though we've not been able to grade perfectly, even though we have quite a poor correlation between our indicating property and grade determining property, we have actually increased the characteristic value of the stuff that's passing the grade compared to the stuff that's failing. So that's the basis of grading, whether it's machine grading or visual grading. With a machine, you have a lot more freedom as to what you're using for this indicating property, and a lot more freedom as to where you set the threshold. In visual strength grading, you might have set limits for ring width and knot size and so on, so you might not be able to position this exactly where you want. So usually the case is that you have certain rules for visual strength grading, you apply them to a population of timber, a certain species in a certain growth area, and you see what you end up with. You test the timber and you see what properties you end up with, and then you decide how that fits onto a strength class. With machine strength grading, you can actually target a specific strength class and set your threshold accordingly in order to get it. So visual strength grading, you could only produce a certain number of fixed outcomes, like fixed strength classes options. So if you have in mind that you want to use visually strength graded timber of a certain species from a certain growth area, you need to see what strength classes are possible for that population. You can't have anything you like. You're restricted in your options. Whereas with machine strength grading, you can adjust this threshold more freely and get pretty much whatever combination of strength classes you like. The operating principles of machine strength grading are quite varied. We have many different operating principles for machines now in Europe. The old kind of grading machine was physically bending the timber, passing it between 3 rollers, and applying either a fixed force or a fixed deflection, and measuring the stiffness of the timber in the minor axis. So normally when we're testing timber, we test it in the strong axis. We test it that way up. But the bending machine, strength grading machines test it about the minor axis. They test it as a board rather than as a joist. So they're measuring the stiffness, and the lowest stiffness within the length of the timber is indicative of the strength. So that's how those work. The modern way of using stiffness to do your grading is to use acoustics, and there are two main types. There's time of flight, where you take your piece of wood and you apply a stress wave to one end, and you time how long it takes that stress wave to go to the other. So you can hit it with a hammer or use some kind of ultrasonic transducer to send a stress wave down the timber, and you time how long it takes to go to the other end, so you end up with a stress wave velocity. And all materials have to follow this rule, the Newton-Laplace equation, which is that a dynamic stiffness is the density times the velocity of sound in the material squared. That's not a special equation for timber, but it works very well for timber. So that's a time of flight measurement, but actually most of the machines in operation use a vibration method instead. So they hit the wood, usually on the end, but sometimes in a flexural mode. If you hit it on the end, you cause it to vibrate. You get a certain frequency of vibration, a certain fundamental mode, and you can calculate the stress wave velocity from the frequency of vibration. That's because of the wave equation. V equals frequency times wavelength. And for the first mode of vibration, longitudinal, the wavelength is twice the length of the timber. So V equals 2FL. Pretty simple mathematics. So that's acoustic grading machines working to measure stiffness and physically bending machines working to measure stiffness. There are some other methods as well. X-rays is a big one. So an X-ray machine scans through the thickness of the board. And in scanning through the thickness of the board, it can measure the density of the clear wood, and it can also see where the knots are. So it can measure something about the size and the position of the knots, and it can make an indicating property as a combination of knot measurements and density measurements. So that's X-ray machines. One of the advantages of X-ray machines is that you can actually grade a board before you cut it up, because you can set the machine to imagine as if it was two separate boards, and you can make a decision as to whether it's worth cutting it up or using it or keeping it as a wide board. So that's X-ray machines. And there is another type of machine which is measuring effectively grain deviation. And most of the machines that do this shine laser dots on the wood. And the dot elongates in the direction of the grain. So by looking at the elongation of the laser dot, you can infer a slope of grain within the timber. So if the laser dot is aligned, it's nice and straight. If the laser dot is at an angle, that's inferring something about the slope of grain on the surface of the timber. And many machines will actually use a combination of all of these different operating principles to try and get a good relationship between the indicating property and the grade determining property in order to get a good yield from the grading.